Welcome to the Deep Dive, where we cut through the noise to bring you the essential knowledge and insights you need. Today, we're pulling back the curtain on a real cornerstone of modern networking, how Ethernet LAN switches actually function. These are the quiet, kind of unassuming workhorses that just effortlessly route your data, whether it's like a critical business report or your latest streaming obsession. They just work, right? Often without a second thought from us. So our mission today is to go beyond that whole plug and play facade and really explore the sophisticated logic embedded inside these devices. We've poured over our source material here to uncover everything from the fundamental mechanics of MAB addresses all the way to the crucial protocols that prevent network chaos. It's a real deep dive into the hidden intelligence making our digital world run so smoothly.
And what's truly fascinating, I think, is how this apparent simplicity conceals a remarkably elegant and robust set of rules. We'll explore the foundational concepts that allow a basic network to operate right out of the box. And then we'll kind of dig into how we can peek under the hood, to verify these processes and troubleshoot when things don't quite go as planned.
Okay, sounds great. Let's unpack the magic and uncover the hidden intelligence inside your network switch. So you unbox a new switch, plug in your devices, power it up, and almost instantly your network just springs to life. There's no complex configuration needed, really, to start forwarding data frames. It's quite a marvel of engineering, isn't it? This effortless functionality, it hides so much complexity.
It truly is. And this apparent simplicity, it's powered by a very precise three-part logic. At its core, the primary job of any LAN switch is to forward Ethernet frames to their correct destination MSC address. Think of it like a highly efficient automated postal sorting office,
Yeah.
It knows exactly which cubbyhole to place each letter in.
Right, like a little traffic cop inside the box. And what are these three fundamental actions that orchestrate this whole process?
Well, first, the switch is constantly making decisions about when to forward a frame to a specific port, or, crucially, when to filter it.
Filter meaning just drop it or not send it everywhere.
Meaning not sending it out unnecessarily.
Yeah.
This is all based on the destination MAA address in the frame. Second, it prepares for future frames.
Yeah.
It does this by diligently learning the source MA address of every single frame it receives.
Okay.
It's essentially building its own dynamic map of the network. And third, and this is really critical, it cooperates with other switches using something called the Spanning Tree Protocol, or STP.
STP, right. Heard of that.
Yeah, it actively prevents network crippling loops. So that first action, forwarding or filtering, that's its ultimate goal, you could say. The other two are really supporting that core mission.
Okay, and here's where it gets really interesting, I think. These decisions are entirely driven by the source and destination MA addresses. Those are found in each frame's Ethernet header, right?
Exactly.
These unique, permanent identifiers assigned to every network device. They act like the indispensable street addresses for every piece of data on your local network. How does the switch actually learn and use these addresses? That's the key.
That's the heart of it, absolutely.
Yeah.
So imagine our switch starts with a completely empty internal address book. We call this a Kuhn address table.
Okay.
You might also hear it called a switching table, maybe a bridging table, or sometimes even a CAM table, content addressable memory.
Right.
This table is how the switch dynamically builds its knowledge base. It figures out where every device on the network actually lives port-wise.
And crucially, we, as the network admins, we don't have to manually type in all these entries.
Oh, goodness.
That would be an impossible task in any, reasonably sized network.
Absolutely impossible. The genius of it is that switches learn these MO key addresses dynamically, autonomously. When an Ethernet frame arrives on a specific switch port, the switch immediately examines the source MA key address of that incoming frame.
The source, okay. Not the destination yet.
Not for learning, no. The source. If that particular MBA address isn't already present in its address table, the switch intelligently creates a new entry. It associates that MBA address with the precise port it just arrived on.
So let's say Fred, his device has MBA address ending in 1111, sends a frame from port fast Ethernet 01. The switch immediately goes, okay, Fred's MC is reachable out F01.
Exactly. Adds it to the table.
Then if Barney, with his MSC ending in 2222, replies from fast Ethernet 02, the switch learns, and Barney's MAC is out F02.
Precisely.
It's basically building its own real-time GPS system for data packets.
That's a great analogy. And this dynamic learning, it's incredibly powerful. Once an entry for a destination, MA address is in the table.
Which it learned from a source address earlier.
Right. Once it's there, the switch can make a swift and precise forward versus filter decision for what we call known unicast frames.
Known unicast. So frames going to one specific device that the switch already knows about.
Exactly. Frames destined for a single device whose MC address is already listed in its table. So for instance, if Fred sends a frame explicitly destined for Barney's MC address, and the switch's table clearly shows Barney is on port FO2.
Which it learned when Barney replied earlier.
Correct. The switch will forward that frame only out FO2.
Mm-hmm.
And it actively filters it, meaning it doesn't send it out of all the other ports.
That's the efficiency part.
That's where the efficiency really shines.
Yeah.
It ensures traffic goes directly where it's needed, minimizing unnecessary chatter and congestion across the network.
This distributed intelligence, it gets even more fascinating when we bring in multiple switches, right? Like, if Fred is on switch 1 and needs to send something to Wilma, who's connected way over on switch 2.
Right.
Each switch doesn't know the whole network map, does it?
No, and that's the beauty. Each switch independently consults its own MC table. Switch 1 just needs to know which port leads towards switch 2 to reach Wilma. So SW1 forwards it to SW2, probably over an uplink port. Then switch 2 receives it, looks at its own internal map, sees Wilma's on one of its local ports, and forwards it directly to her.
So each switch is just a local expert.
Exactly. They collectively form this larger interconnected system without needing any single central controller. It scales really well.
Okay, that makes perfect sense for known devices. But what happens when, the switch gets a frame and the destination, a MASI address, just isn't in its table yet? Like, imagine Fred sends his very first frame to Barney, and the switch's MASI table is completely empty. It can't look up an address that isn't there, right?
Correct.
This feels like a moment where the whole system could just, I don't know, grind to a halt.
Yeah, you'd think so, but this is where a crucial fallback mechanism kicks in. It's known as flooding.
Flooding, okay.
When a switch receives an unknown unicast frame, meaning it's going to a single device, but that device's MSC isn't in the table. Yet it takes a strategic approach. It forwards copies of that frame out all other interfaces, every single one, except, of course, the one it originally received the frame on. You don't send it back where it came from.
So if it doesn't know where to send it, it basically shouts out, "Is anyone here, Barney?" by sending it everywhere.
That's pretty much.
That sounds like a brilliant, if maybe slightly noisy way to discover devices.
It is. The core idea is simply to guarantee that the frame eventually reaches its intended destination. And here's a really clever part.
There's more.
When that destination device, Barney in our example, finally gets the frame and sends a reply.
The switch sees the reply coming in.
Exactly. It sees the reply coming in on a specific port, looks at the source MSC address of that reply, which is Barney's MSC, and then it learns it.
So the reply teaches the switch where Barney is.
Precisely. It adds Barney's MSC and the associated port to its table. From that point on, all subsequent frames destined for Barney become known unicasts.
And they get forwarded efficiently just to Barney's port.
Exactly. The flooding stops for that destination. Now, switches also flood broadcast frames.
Right, things meant for everybody, like DHCP requests, maybe.
Good example. Yeah. Frames intended for all devices on the LAN. They have a special destination MC address, all Fs usually. Those are always flooded out all ports, again, excluding the incoming one, to ensure every device gets a copy.
Okay, so this shout-it-out method, the flooding, works beautifully for discovery, ensures even unknown devices eventually get their messages. But imagine the sheer chaos if our network has multiple physical paths between switches. We often build networks like that, with redundant links for reliability.
For fault tolerance.
Yeah.
Very common.
Sending things everywhere when there are loops. That sounds like it could quickly spell disaster, couldn't it?
You've absolutely hit on a critical point. While redundant links are fantastic for reliability, yes, they are indeed a nightmare for flooded frames.
Yeah.
A complete nightmare. If Larry sends an unknown unicast frame to Bob in a network with redundant links, but crucially, no spanning tree protocol running, that frame would essentially loop around the switches forever. It gets flooded out one port and rise back in another switch, gets flooded again.
Oh, wow.
Constantly reflooded.
Okay.
It creates what's often called a broadcast storm. It just multiplies exponentially, quickly congesting the entire LAN, chewing up all the bandwidth and CPU on the switches, and basically rendering the network completely unusable.
Yikes.
This is precisely why loop prevention isn't just important, it's absolutely fundamental to a stable switch network.
Okay, so this raises the obvious question. How do we get the benefits of redundancy, those backup routes, better uptime without the absolute chaos of endless loops and a network meltdown?
That is the powerful and frankly ingenious role of the spanning tree protocol, or STP.
Okay, STP to the rescue.
Pretty much. STP actively uh, figures out the network topology, and then it blocks some ports on switches from forwarding frames. Logically blocks them. It does this in a way that ensures there's always and only one active logical path between any pair of LAN segments or switches.
One path, even if multiple physical paths exist.
Exactly. This prevents those devastating loops, keeping the network stable and preventing that storm-based congestion. An interface that STP puts in a blocking state won't forward or receive user data frames, whereas one in a forwarding state operates normally. I remember a case early in my career where someone accidentally or maybe intentionally disabled STP on a couple of core switches because they thought it was slowing things down.
Oh, no.
Within minutes, the entire campus network just melted down into a screaming broadcast storm. Total chaos. It was, let's say, a very practical lesson in just how vital this quiet background protocol really is.
Wow. That's a powerful reminder. Sometimes the most invisible components are the most critical. But okay, the elegance of STP, creating that single logical path, it comes with an interesting trade-off, doesn't it? If it's blocking links, aren't we losing some of our potential bandwidth? We paid for those links.
Well, that's a very fair point. You're absolutely right. To guarantee that loop-free topology, STP intentionally blocks redundant links from actively forwarding user traffic. While this prevents the network collapse, it absolutely means we're not utilizing our full potential bandwidth on those blocked paths for everyday traffic.
So they just sit there, idle, waiting.
Pretty much, yeah. Waiting for the primary path to fail. Furthermore, there's the issue of convergence. That's the time it takes for STP to detect a failure on the active path and then reconfigure the network to unblock and activate a backup link.
And that takes time, right? It's not instant.
Traditional STP could take, 30 to 50 seconds, which in network terms can feel like an eternity. This convergence delay can introduce noticeable interruptions.
Which led to improvements, I assume.
Exactly.
Yeah.
This led to the evolution of protocols like Rapid Spanning Tree Protocol, RSTP, and others. They were designed specifically to significantly speed up that healing or convergence process.
Making failover much faster.
Much faster, yeah. Down to a few seconds, or even less in some cases, which is critical for modern high-availability networks where, every second of downtime really counts.
Okay, so putting it all together. These three core functions, intelligent forwarding based on learned addresses, the dynamic MSE learning itself, and robust loop prevention with STP, or RSTP, they're all working tirelessly behind the scenes. Our source material confirms that switches, like Cisco Catalyst switches, for example, they come with these essential features enabled right out of the box, by default.
That's right.
Interfaces are up, everything's initially in VLAN 1, auto-negotiation is usually on to figure out speed and duplex, and all the MA learning, forwarding, flooding logic, and STP are just ready to go.
Yep, it really is designed to be plug-and-play for basic functionality.
It truly is.
And for those of you listening who want to actually see this hidden magic in action, you could absolutely use specific commands on the switch's command line interface, the CLI.
Ah, the fun part.
Indeed.
Yeah.
For instance, to view that dynamically built internal address book showing the learned MAC addresses and which port they're associated with, you'd use the command show MAC address table dynamic.
Show MAC address table dynamic. Got it.
That gives you a real-time snapshot of what the switch currently knows about device locations.
So if Fred's M key address ending in 1111 is on fast Ethernet year 1, that command would clearly show that entry. It would also show the VLAN, which is usually VLAN 1 by default, right?
Correct. It typically shows the AMP address, the type dynamic, the VLAN ID, and the associated port.
And this also highlights a really crucial point you touched on earlier, switches forward frames within a VLAN. So this MAC address table, it's not just one big table for the whole switch, is it?
Excellent point. No, it's not. It's critical to remember that this MAC address table is actually built and maintained per VLAN.
Per VLAN, okay.
When Fred's NC is learned on port FO1 in VLAN 1, the switch knows to only forward traffic destined for Fred within that specific VLAN 1. If there was a Fred clone in VLAN 10 on the same switch, it would be a separate entry.
Ah, I see.
This fundamental design choice is what allows us to logically segment traffic on the same physical switch hardware. It gives us both enhanced security and more efficient bandwidth use without needing, separate physical switches for each department or traffic type.
Makes sense. So these MAC table entries, do they stay there forever, or do they eventually disappear? Like, what if a device moves from one port to another? Does the switch get confused, or is it smart enough to update its address book on the fly?
Good question. No, they don't stick around forever if the device goes quiet. Switches employ an aging time.
An aging time.
Yeah, exactly. It typically defaults to 300 seconds, which is 5 minutes, on many switches. If a frame from a specific source MAC address isn't seen again within that time frame,
So 5 whole minutes.
then its entry is automatically removed or aged out from the table. However, the timer resets back to 0 every single time a frame is received from that source, MA.
So active devices stay in the table.
Correct. This aging process is vital for keeping the table clean and relevant. But, it also creates some interesting challenges sometimes. Imagine a device that sends traffic very infrequently, maybe a sensor that only records in once an hour.
Right.
If the aging time is 300 seconds, its MAC table entry will definitely expire between transmissions. So each time it sends data, the switch will have to relearn its location, leading to a temporary unknown unicast flood for that first packet each hour.
Ah, okay. So you might need to adjust that timer sometimes.
Exactly. Tuning the aging time can be a critical administrative task in specific environments, though often the default is fine. And if a device moves ports,
Yeah, what happens then?
the switch handles it gracefully. The old entry for the original port will eventually age out because no more traffic is coming from that MAC on that port. And as soon as the device sends traffic from its new port, the switch learns the new location and updates the table.
Or rather, adds a new entry.
Adds the new entry,
Yeah.
correct. So the network essentially self-corrects its knowledge. And the table itself isn't infinitely large either. It has a finite size. Maybe around 8,000 entries on a typical Catalyst switch, depends on the model.
Only 8,000. What if it fills up?
If it fills up, which can happen in very large layer 2 domains,
Yeah.
the switch usually purges the oldest entries, the ones that haven't been heard from in the longest time, to make space for new ones being learned.
Okay, oldest out first.
Generally, yes. And if you ever need to, maybe for troubleshooting or after making network changes, you can manually clear out dynamic entries using the clear MAC address table dynamic command.
Clear MAC address table dynamic, okay.
Yeah, and there are options to clear just for a specific VLAN or specific interface, or even just a single MAC address if you need to be surgical.
That makes perfect sense. You don't want stale information cluttering up the address book if a device moves or is disconnected. The aging time provides that crucial self-healing. Okay, beyond the MAC table, what other commands are essential for just quickly checking the pulse of your switch? Basic health checks.
Well, a really common one is show interfaces status.
Show interfaces status.
Yeah, that gives you a quick overview of all the ports, showing if they're physically connected or not connect, what VLAN they're in, their speed, duplex, and type. It's often the very first step in basic connectivity troubleshooting. Is the light green? Is the switch seeing the connection?
Good starting point.
Definitely. And if you want to see detailed statistics about the traffic actually flowing through a specific port, like counts of incoming and outgoing frames, unicast, multicast, broadcast, errors, maybe the show interfaces, interface aid counters command is invaluable.
Show interfaces counters. Okay, so you'd put in show interfaces fast Ethernet 0-1 counters.
Exactly. It tells you precisely what traffic is flowing, how much, and if there are problems like errors or discards. Really useful for pinpointing traffic anomalies or performance issues.
What if you're dealing with a really massive network, maybe thousands of MK addresses spread across many switches and VLANs? Finding one specific entry in that long show MAC address table dynamic output sounds like, well, a nightmare.
Been there?
I've definitely been there, scrolling through pages and pages of output trying to find one device.
Yeah, it can be painful. But thankfully, the command line is smarter than just dumping everything. You can filter the output of show MAC address table dynamic to pinpoint exactly what you're looking for.
Filtering options. Good.
You can filter by a specific MIC address using address followed by the MAC. So show MAC address table dynamic address 020.100.100.111.
Okay, straight to the point.
Or you can filter by interface, like show MAC address table dynamic interface fast Ethernet 01 to see only the AMACs learned on that port. Or even by VLAN, using VLAN followed by the VLAN ID, like show MAC address table dynamic VLAN 10 to see all dynamic AMs learned just in VLAN 10.
Those filters sound indispensable for troubleshooting in larger environments. Saves a lot of scrolling.
Absolutely. Essential tools for quickly zeroing in on the information you need when you're trying to figure something out in a complex network.
So let's tie this all together. What does this all mean when we scale up, when we have multiple switches, like in a bigger campus network or a data center LAN? How do all these independent switches work together to form one cohesive, functional, large-scale network?
Well, as we touched on, it's really a beautifully distributed system. If we connect two switches, let's call them SW1 and SW2, maybe with a trunk link between them, each switch still operates independently. building its own MAs table based on the source addresses it sees. SW1 learns the MA sees a device is directly connected to its local access ports, say SO1 and SO2. It also learns that any MC addresses connected over on SW2 are reachable via its uplink port to SW2. So let's say that's Gigabyte Ethernet 01, G01.
Mm.
So we'll have multiple MAC entries pointing to G01.
Okay, so it knows the direction to reach those remote MAs.
Exactly, the direction, the next hop switch, essentially.
Yeah.
Similarly, SW2 learns the MACs connected locally to its ports, maybe FO3 and SO4, and it learns that devices connected over on SW1 are reachable via its link back to SW1, maybe G02 on its end.
Got it. They each build their own perspective.
Precisely. The really critical takeaway here is that each switch's MZ table lists the location of devices relative to itself. They don't share some single global MA table in the sky.
Right.
Rather, they collectively build their individual knowledge bases based on the traffic they see. It's this decentralized yet perfectly coordinated approach based on these simple rules that allows them to forward frames efficiently across the entire LAN fabric.
And that's a key reason why Ethernet networks are so scalable and resilient, I suppose. No single point of failure for the control plane, really.
Exactly. It's built right into the fundamental logic.
Wow. It's truly incredible how much intelligent, self-organizing logic is packed into a device that, for the most part, performs so reliably right out of the box. We've seen how switches dynamically build their knowledge base, how they efficiently direct traffic just where it needs to go, and how they crucially prevent network meltdowns using STP, all through a few fundamental rules based on those unique MA addresses.
And if we connect this to the bigger picture, it really highlights how foundational these layer 2 switching concepts are. They apply to any network, really, from a tiny home office setup to a massive global data center. Understanding these processes isn't just about knowing what your network is doing, but fundamentally why it's doing it.
Yeah, the why is key.
That understanding is absolutely critical for effective network design, for performance optimization, and of course for troubleshooting when things inevitably aren't flowing quite as expected.
So, thinking about all this, what really stands out to you after diving deep into the inner workings of Ethernet switches? Maybe it's the sheer simplicity and elegance of the dynamic MS learning, or the absolute necessity of something like STP, even if it seems counterintuitive to block links. Or maybe just how much complex stuff is going on behind the scenes just to keep your internet humming along without a glitch. As you, listening, continue to navigate the increasingly complex world of technology, maybe consider this. The simple, independent logic of a network switch allows a massive, interconnected system to function with surprising resilience. How many other seemingly simple, everyday systems in our world rely on similarly powerful yet often hidden foundational rules? It's definitely